Okay, everyone. This example just continue showing calculus center of mass in a continuous system. And last video we show you a uniform rod. Okay, uniform rod. Okay, and now we just change the problem a little bit. Now the rod density is not uniform. Okay, and its line density is alpha times x. X is a coordinate. X coordinate. Okay, x the coordinate. Okay, alpha is arbitrary constant, and the length and the mass of the rod are the same with the same as the last problem. Okay, length of the rod is capital L, and the total mass of the rod is capital M. Okay, and in this question, answer to this problem, we want to calculate first of all find the alpha. And the second question, find the center of mass of the non-uniform rod. Okay, so let's find out alpha first. Okay, because alpha is arbitrary constant, but we can find alpha alpha based on the information of this question. Okay, how to get alpha? We start from this line density. Okay, and in the last problem, I say in the continuous system, okay, analysis, we just slice a little bit. This is called delta m, and the delta m, its length is delta x. Okay, and the coordinate system is because we also assume it's a one-dimensional problem. So the origin is here, and this is x direction. Okay, okay. So how do we find alpha? We will use the concept here. Okay, suppose I summation all tiny delta m together. What will we get? Because we summation all delta m together. Okay, yeah, because integration is just a summation, another representation of summation. Okay, that means so delta m is very tiny, but still greater than zero. Okay, and you can add all of them. That's called an integration. If you summation all delta m in this range, 0 to L, okay, that's it's 0. And that's very information. Okay, because the length is L. Let's add all these small elements between the 0 to L and add this small tiny delta m together. What will we get? We add the tiny mass together and we will become a total mass. And total mass is a capital M. Total mass is a capital M. So it's equal to delta M. And we can use this equation to find alpha. Okay, how? Okay, in last video I say delta M, this integration, we need to find a relationship between the delta M and delta X. Okay, relation between delta M and delta X. Mhm. Between delta M and delta X dx. And the last time we say what's the delta M? And delta M is equal to line density, line density M times and delta X. Okay, line density times the L times the length is equal to mass. Okay, and the line density here is not uniform anymore. It's alpha x. Okay, so it's equal to alpha x times dx. Okay, so we find a relationship between the delta m and delta x. So let's put this back to in this equation what we have. And this integration has a range, so 0 to L, and delta M is alpha x dx equal to capital M. And alpha is, I say, alpha is arbitrary constant, so alpha can factor out, so 0 to L, x dx equal to M, capital M. So alpha is equal to, because it's a power function integration, I suppose you already know the power function integration. So it will become this one, 0 square equal to M. Okay, and we have alpha L squared over 2 equal to capital M. So what's our alpha? Our alpha is L squared 2M over L squared. Okay, that's alpha. That's the first problem. Okay, alpha is 2M over L squared. Check my answer. Did I calculate right? I'm afraid I calculated wrong again, right? Mm, yeah, 2M over L squared. Okay, that's true. Okay, so, and the second question, what's the center of mass of the rock? Okay, for center of mass, to remember that it's a one-dimensional problem, okay, and it's also continuous system. So, what's the formula? Do you remember that? It's 1 over capital M. Its total mass is M, and its integration x delta M. Okay, and 1 over capital M, that's no problem. So the integration here, yeah, we have the range 0 to L. Be careful, 0 to L. And X, okay, you just leave it here. Okay, don't do anything. And delta M, we say delta M is equal to line density times delta x dx. So it's alpha x dx. So delta M is alpha x dx. Okay, so yeah, it's finished. Okay, we finished. And let's see, because alpha is 2m divided by L 2m over L squared. So if alpha is here, we can constant, we can factor it out. So it's 1 over capital M. So it's L squared 2m. And inside we left x squared dx. Okay, it's still a power function in the equation. I suppose you familiar with already. So this can, okay, 2L square, and this will become, I hope you understand, really understand the integration of power function, 3. Okay. So it's L square 2, 3, L3. So, okay, so it's 2 over 3 L, 2 over 3 L. Okay, so its center of mass, I think, so in this non-uniform, the center of mass is 2 over 3 times L. So it's maybe roughly 1, 2, 3, maybe just probably here. Okay, center of mass probably here. Okay, it's not right at the middle anymore. Okay, because its density is not uniform, and we look at its density. Its density is a constant times x. Why become this? It's its line density is alpha times x. That means if you have if x value, that means that if your coordinate value is up, your mass is also increased. Okay, this is what it means when you if so it means your x coordinate is higher. That means you have a higher mass. Okay, that's this line density means. So the mass will here and then here. So let me draw this. Okay, alpha times x. So you look at this here. The line density is low, but as the x coordinate increase, the line density will gradually increase. Okay, okay, okay. Here at the origin, the line density is low, but it will increase as the coordinate increase. So the mass will. So you intuitively the mass distribution or most of mass will distribute build at the right hand side of the at the right hand side of L over 2 because most of mass will distribute here. Okay, because its mass distribution is alpha times x, so it will most of mass will distribution a large value of x. So the center of mass of this non-uniform rod is no longer L over 2, no longer right at the center of the rod. It will shift to the right hand side. Okay, because of this non-uniform density. Okay, Okay, so the answer is 2L over 3. That's very reasonable. Okay, because it distributes at the right hand side of this rod. Okay, it's located at the right hand side of this rod. Okay, so this is another example for calculus center of mass using the in the continuous system and non-uniform density. And next video will demonstrate example on the textbook. And in the textbook, it use actually it's a two-dimensional problem, but after all, it's still reduced to one-dimensional problem. Okay, but I will talk about discuss the problem in the next video. So see you in the next video. Bye bye.